Thank you for the introduction. Sorry, it's a little bit concentration. Hello, everyone. This work is together with Lili Wang and Xuefeng from Beihang University, and with Voicu Popescu from Purdue University. Occlusions abound in our real and virtual 3D worlds. They make VR exploration complex, since we have to navigate around occluders to see the parts of the scene that they hide. So our motivation is to devise visualization schemes that assist the user with the problem of occlusions. But how can we achieve this? There are some challenges that have to be overcome. First, given a 3D scene and a user view, how can we find where occlusions occurs? Once we find where occlusions occur, how can we model the disocclusion process that is conductive to ultimately removing the occlusions? One approach for handling occlusions is to render occluders transparently, like in X-ray or cutaway visualization. Another is multiperspective visualization. This method shows the entire side corridor to the user from their current location. In this previous work, the disclusion effect was modeled by hand with a rectangle that maps to the side corridor portal. Our paper automates the process of finding, modeling, and removing occlusions. Top left shows the overview of our method. First, the scene is rendered conventionally. And then our method detects occlusions by finding depth discontinuities on the center line of the depth buffer. Here, the red dots show near to far silhouette points. Green dots show far to near silhouette points, and black dots show inflection points. Red dots are only detected in the left side of the image, where the disocclusion effect will be negative with the small head translation to the right. And similarly, green dots are only detected in the right side of the image. The depth discontinuous points are used to construct the disocclusion portals. A disocclusion portal is a vertical planar contour that starts from a silhouette point to ensure this portal is binding with a potential occluded area. Given a silhouette point, several candidate portals are considered. Here, the candidate portals for the red silhouette point A are AB1, AB2, and AB3. Each is defined by a green silhouette point or an inflection point. I will get back to portal selection a little bit later. Here, the best portal is AB2. The disocclusion portals are used to build a graph camera, which will ultimately be used to render the multi-perspective visualization. Here, the portal AB is used to define a hinge plane where the visualization transitions from viewpoint V to viewpoint V prime. The rays are piecewise linear with two segments. Point P is projected directly to the point P prime with a compound projection matrix that accounts for the two viewpoints. The magnitude of the disocclusion effect is controlled by placing the secondary viewpoint V prime. It's left up to the user, who controls the disocclusion effect with the small head translation. The available disocclusion portals are shown to the user, who selects one or several portals and then triggers and controls the disocclusion effect. This figure shows a single portal selected, and this figure shows multiple portals selected by the user. Here is the disocclusion effect achieved for the single portal. The disoccluded region is highlighted in red for the purpose of this presentation. This figure shows the disocclusion effect for the multiple portals. This video shows the merged disocclusion effect of 4 portals. When user translates their head to the right, left portals shows the disocclusion effect, and when user moves their head to the left, right portals shows the disocclusion effect. Here is another look at our portal selection. When we're choosing portal AB1, the portal image footprint is too small to show the disoccluded part of the scene at adequate resolution. And when we're choosing AB3, the footprint of the portal is large, but it introduces substantial distortions. And when we're choosing portal AB2, it offers a good compromise of the 2 antagonistic requirements. Our method can also handle dynamic scenes. Here, the carriage starts from the left side of the image. And this figure shows the corresponding disocclusion effect. The conventional rendering and the corresponding disocclusion effect. And then the carriage moved to the right side of the image. And the disocclusion effect also changed to catch up with the moving carriage. And this is the conventional rendering after moving and the corresponding disocclusion effect. We also conducted a user study to evaluate the effect of our method. One is to find stationary vehicles in a desert village. Here, the user finds a hidden blue car using our disocclusion effect. The other is to catch up with a moving person in a Chinese garden. Here, the user uses our method to see the inner yard from afar. We measured performance with several metrics. One metric is the total viewpoint translation in meters. Our method reduces viewpoint translation by 60%. The difference is significant. The effect size measured with coherence D is huge. Another metric is total view direction rotation, which is also significantly reduced when using multiperspective visualization. Since the user can preview for faraway regions of the environment without having to actually go there, the number of times redirection is needed to avoid the boundary of the tracked area is reduced as well. Finally, participants in the experiment group complete the task faster. These figures are averages over the 2 tasks. We also conducted perceptual experiment to evaluate the impact of our method on spatial awareness. In a depth estimation task, participants were asked which of the red and green sphere is farther. Control group participants see both spheres directly as shown here. Experiment group participants cannot see the spheres from the conventional view, and they have to engage the disocclusion effect to see them. In addition to depth estimation, we also gauge situational awareness with a pointing task. Control group participants start from the view shown here. Then they are told to walk to the red balls from where they can see the hidden green sphere, as shown here. Finally, they are instructed to walk back to the initial position, and they are asked to point to the new hidden green sphere using a tracked controller. The difference between the pointed and correct direction defines the pointing error. In experiment group, participants deploy the disocclusion effect to see the hidden green sphere for a short while, and then the disocclusion effect is retracted. Finally, they are asked to point to the hidden green sphere. Here are the results of the 2 perceptual experiments. The difference between conventional and multi-perspective visualization is not significant, meaning that our method does not significantly degrade spatial awareness. We have also investigated simulator thickness, and the post-experiment total scores are not much bigger than the pre-scores. In conclusion, we presented an automatic method for managing occlusions in VR scene, which increases scene exploration efficiency while preserving spatial awareness and brings only modest simulator thickness increase. One future work is to quantify the amount of occlusion in a conventional visualization frame and provide occlusion guarantees. Another is to address fine-grained occlusions to further improve the disocclusion capability of our approach. And thank you.
Other questions? Okay, so good. But I have one. Yes. So when you see the video, what came to my mind is, of course, a question how good you are as a user in getting orientation, a mental map of the environment using your method. Yes. So as far as I understood, your evaluations didn't look too much into detail regarding orientation. But I was wondering whether you think that will have a negative effect or no effect on building a mental map of your environment using this method, so being able to navigate in the end.
Yes, I think with our method, the scene is gradually changed to when we see the occlusions. So we actually know the change in this thing, so we can have a good mental map of this thing. So yes.
Is that something you will be investigating in future?
Future we have some progress in quantify the occlusions in the scene. So we want to know the disoccluded part in the current view, and we can decide which part of the occlusions is more interested to the user, so we can get into that occlusion. Now we have a great solution.
Good. Any further questions? No? Then let us thank the presenter again. And the next presentation will be a conference paper.